Hi everyone, welcome back. This is part 2 of our discussion of inferential statistics. And this portion we're going to focus on hypothesis testing, which builds on what we were talking previously about inferential statistics related to confidence intervals, using some of the same logic regarding probability distributions. However, our goals are very different when we start to do hypothesis testing. So hypothesis testing, again, is the second major use of inferential statistics, which is why we're covering it this week, because it is related to what we were discussing with confidence intervals. Hypothesis testing uses the laws of probability to help researchers make objective decisions about accepting or rejecting a null hypothesis. We're going to talk about what the null hypothesis is here momentarily. Usually, researchers are interested in finding differences between two or more groups, while the null hypothesis is that there's no difference. And we'll see why this kind of quirky logic is used here momentarily. So the null hypothesis in most bivariate studies, the null hypothesis states that the variables in the study are equal and are not associated with one another. So examples of a null hypothesis would be the cigarette smoking is unrelated to lung cancer, or turning patients is unrelated to the incidence of pressure ulcers, or height is unrelated to weight, okay? It's the exact opposite of what we would expect or we might anticipate as a reasonable research question or a reasonable relationship that we might expect to see. So why do we do it backwards? Well, we're trying to set up a test that will tell us how likely it is that there is actually no difference. How likely is it that the null hypothesis of no difference is likely to be true? So the logic of it is a little bit backwards, which is going to be a leap for some of you, but there is some solid ground here, because our research and alternative hypothesis is the direct contradiction of what the null hypothesis is. The null hypothesis contrasts directly with our research hypothesis. We would say that cigarette smoking is related to lung cancer. Turning patients is related to the incidence of pressure ulcers. Height is related to weight, or those might be our hypotheses. So the null hypothesis in general is going to be that there is no association, that the means are equal, that there's no correlation, that there's no difference among our groups. That's the null hypothesis. And the word null actually means zero. So if you think of null meaning zero, it's a lot easier to remember what the null hypothesis means. It's not named for someone like most of the stuff in statistics is. So hypothesis testing logic, as though it often feels backwards, it's similar to the concept of innocent until proven guilty, which comes from jurisprudence. So we want to have enough evidence to reject the null hypothesis of no difference before concluding that there is a difference. Okay, so we need enough evidence from our data to reject the null hypothesis of no association, of no difference. It's a conservative approach that puts boundaries around what is considered sufficient evidence based on probability. So we could think of it as the default. The default is no difference. We need enough evidence to prove otherwise. Formally, we are asking how likely is the null hypothesis to be true given the observed data. So if we have two sample means, two groups that we're comparing, and they're widely different, how likely is it that there's actually no difference if we were to get two sample means that different? That's exactly what we're going to look at today. So there is a direct link between probability and hypothesis testing. And one way to think about this is that when we were talking about the deck of cards and we were wanting to test a null hypothesis that the deck is fair, meaning that there's nothing faulty with the deck, no tricks being played here. We're going to say that the null hypothesis is the deck is fair, that it's not rigged. Our alternative hypothesis is that the deck is rigged, okay? So we're going to say innocent until proven guilty. So what is the probability of drawing 10 red cards in a row if the null hypothesis of it being a true deck or a fair deck is true? Okay, we can actually calculate that directly. It would be 0.50 times 0.50 times 0.50 as we did last time. Okay, the probability of getting 10 red cards in a row would be 0.001. Okay, so that would be less than 1% or a tenth of a percent. So only 1 in 1,000 draws of 10 cards from a fair deck of cards would yield all red cards. So we're already at a point, if we did find 10 cards in a row, red cards in a row, we'd say, wow, that's not very likely to be a true deck of cards, or maybe you didn't shuffle appropriately. But though we cannot say definitively that the deck is rigged, there is only a 0.001 chance or a 0.1% chance that the deck is not rigged. Okay, so we're going to assume that it's not. And how much evidence is that there that it is not rigged? And here it sounds like we got 10 in a row. It's highly unlikely that it's not either rigged or poorly shuffled. So researchers do not seek to prove their research hypothesis is correct or incorrect, but we are going to use the laws of probability to make decisions about whether the null hypothesis is probably incorrect at specified levels of probability. Okay, so the rejection of the null hypothesis lends support to the alternative hypothesis or the research hypothesis. We don't say that we've proven or this shows that our hypothesis is true, but if we can reject the null hypothesis of no association, we can say that it's very unlikely that there's no association. Therefore, there is an association between two variables. So when we conduct research, there are 4 possible outcomes in terms of our ability to make inferences and making errors in inference. 2 are good and 2 are bad. And we're going to try to optimize the likelihood that we're going to fall into the first 2 rather than the second 2 when we do research. So one outcome would be we fail to reject the null hypothesis when the null hypothesis is true, meaning we have a true negative finding. Okay, the null hypothesis is true. There's no difference in the population. And we also fail to reject that null hypothesis. We didn't find enough evidence to suggest that the null hypothesis is not true. That would be a true negative finding. Okay, that does happen, and we should report out that information, just as we would a positive finding. We can also reject the null hypothesis of no association when the null hypothesis is not true. And that would be a good finding in that it's a true positive. The null hypothesis is not true. There is a difference. And we rejected the null that there is no difference. So we were correct. Okay. So I know the logic here is a little elusive, but bear with me. So we could also reject the null hypothesis when in fact the null hypothesis is true. This would be a false positive result. We're saying that something is statistically significantly different, and yet if we would have continued to draw bigger samples or we had done a different study, we would find that nope, turns out there's no difference, okay, let's say between 2 groups. And that would be a false positive finding. We want to avoid doing that with statistic. We could also fail to reject the null hypothesis when the null hypothesis is false. Okay, null hypothesis being false means that there is a difference and we didn't find it. Okay, this often happens when we don't have a big enough sample to detect a difference when there was a true difference in the population. This would be called a false negative finding. Again, we're going to try to minimize as much as we can committing any of these kinds of errors of inference. And there's ways that we can do this. First, we need to talk about this a little more specifically. We have what are called type 1 and type 2 errors. You can also think of these as alpha errors and beta errors. Type 1 error or alpha error is the null hypothesis is actually true in the population, but the researcher rejects it. Okay, we incorrectly rejected the null hypothesis. We found a result that was false. Okay, or I should say that we concluded that there was a difference, let's say a treatment effect, and in fact there was no effect in the true population. That would be a type 1 error. We want to avoid that as much as we can, and that we do by setting our alpha level or our level of significance. And we might set alpha at 0.05, for example. We'll talk more about that in a moment. Type 2 error or beta error is that the null hypothesis is actually false in the population, but the researcher accepts it. We incorrectly accepted the null, meaning we didn't find any difference in our study, but yet there is a difference in the population. Okay, and so we don't really know whether we're making these types of mistakes of inference unless we were to continue to take other studies. However, we can minimize our risk of making a type 1 error or type 2 error. Type 1 errors are controlled primarily through setting a p-value or an alpha level that's conservative enough that we are not likely to have a false positive result. The probability that we set is going to be one way that we can control the likelihood of having a type 1 error. By convention, we often use 0.05. There are other reasons to use other values, but basically we can set that value at a certain level. The level of significance, or alpha, is the area in the theoretical probability distribution corresponding to a rejection of the null hypothesis, basically towards the tails of a distribution. In most cases, like I said, we're going to select an alpha of 0.05, which is equivalent to a 5% risk of making a type 1 error. And this is analogous to making a 95% confidence interval. So we know when we calculate a 95% confidence interval, there's a 5% chance that it will not contain the true population parameter that we're trying to estimate. Likewise, when we're making an inference about, let's say, difference between two group means, we set an alpha of 0.05, p less than 0.05. We're saying that we're willing to accept a 5% chance of being wrong. Okay? P-values less than 0.05, we say that we reject the null hypothesis, our data don't support the null hypothesis, and our evidence is beyond a reasonable doubt. Okay? So that's our threshold for saying something statistically significant. Now, this is changing a little bit in the era of big data, because as we get bigger and bigger samples, it's more and more likely that we're going to get a p-value that low. So medical science is still kind of hung up on this 0.05, as we'll talk about, but that's the criteria that we're going to use for saying something statistically significant. For larger p-values that we calculate, greater than 0.05 for significance, you fail to reject the null hypothesis. You don't have enough evidence against the null hypothesis. The probability of the null hypothesis being true is not good enough to reject it. Okay, so if your computed p-value is, let's say, 0.10, it means the null hypothesis has a 10% chance of being true. And therefore, do we want to allow that much risk of being wrong? So p 0.10 is not enough to reject the null hypothesis. We want something that's lower than that to say the null hypothesis is very unlikely to be true given our data. So why p less than 0.05, or why alpha of 0.05? P-values were developed during a time when studies were often based on randomized studies that are relatively small, or observational studies that are relatively small. We still use p equals 0.05 as a cut point. However, as I said, as we move towards using big data and more observational studies, some have begun to question the relevance of using a p-value p less than 0.05. For the purposes of this course, we're dealing with relatively small samples, and so p less than 0.05 is appropriate in most cases. So this is something scientists have agreed upon as being a reasonable value to reject the null hypothesis. And science is self-correcting, and so we wouldn't generally make a decision based on a single study. This is why we often repeat studies. So if we're doing a clinical trial on a new drug, we'll use multiple sites or locations. We'll do multiple studies to clearly, definitively show something to be efficacious or making some kind of difference, right? So we don't rely on the single study, so we're willing to have a certain amount of error of inference. And you've probably seen, likewise, margins of error around estimates that you've seen all the time that has to do with confidence intervals. And like we know that we're not exactly right, but we can say within which bounds of certainty we have estimated some parameter. Type 2 error risk, that's where we fail to reject the null hypothesis, and the null hypothesis is false, meaning there was a difference, but we didn't find out. This is usually designated beta, called beta, and the power of a test, meaning how much are we able to correctly reject the null hypothesis, we could say is 1 minus beta. So whatever we set as our beta would be the power of the test So the power of a statistical test to correctly reject a false null hypothesis, we would say, is 1 minus beta. That would be power. So let's say we're willing to have a risk of 20% of making a type 2 error. Okay, we're going to be a little less conservative. Failing to detect a difference, we're a little more comfortable with that. So we might set beta at, let's say, 0.20. So we would have, in that case, have 1 minus 0.20, that'd be 80% power. So often that's what we want, somewhere in that ballpark. The most straightforward way to increase power is to increase the sample size. So when we do a power calculation in a study, we might determine how much power did we have to reject the null hypothesis. In advance, we may calculate a sample size that we need to achieve a certain power based on what we know already in the population. That can be a little tricky, so usually we err in favor of larger studies, but that's a whole other part of statistics we're not going to get deeply into. But when we design a study, it's not by just however many we can get. Usually we know how many we need to detect an effect of a certain size that we're interested in. Okay, so this gets us to the concept of a critical region of a distribution. So researchers calculate a test statistic based on some area of those distribution curves, those probability distribution curves. And that area in the curve where we reject the null hypothesis is called the critical region. So anything above that on the right end, on the right tail, anything below that value on the left tail, we would reject the null hypothesis. And the critical region is going to vary a little bit depending on our sample size and the type of distribution that we're looking at. So we have what are called a series of t-distributions, all based on different sample sizes, and we have to actually look that up in a table, or we can have our computers calculate p-values for us directly. We don't have to look it up in a table. We're going to do that 99% of the time in this course, and then in the real world, we let the computer do it. But there is what's called a lookup table that you can find out what those critical values are. And if you look at reported statistical findings, you'll often see notation that shows that what the critical region value was, and your test statistic was higher than that value, or absolute value is higher than that critical cut point. So we reject the null hypothesis if the statistics falls at or beyond the critical region on a theoretical sampling distribution for the test statistic. We accept the null hypothesis otherwise. Okay, so when we look something up in the table, it has to be greater than that value if it's positive, or less than that value if it's negative, to reject the null hypothesis. That means it's really towards the tail end of that distribution. So to illustrate the statistical tests, we might say that our critical region in this t distribution, notice that it's not as peaked as a perfect standard normal distribution. It's a little flat, there's a little more area in the tails. And we might then say that, so the steps in doing a manual approach to hypothesis testing is first we select an appropriate test statistic. We do a t-test, we can do an f-test, we can do any number of different types of tests, and we're going to cover t-tests and f-tests in this course. We specify a level of significance, or alpha. We decide on a one-tail test versus a two-tail, meaning are we going to look at possibilities of difference in one direction, or are we going to look at possibilities of difference in two directions? Normally, we're going to do what's called a two-tail test. We calculate a test statistic using appropriate formulas. The formulas tend to be a bit complicated, so we usually let a computer do those. We calculate the degrees of freedom, which is often based on the sample size and the number of parameters that we're trying to estimate, and compare that test statistic to a table value for the appropriate degrees of freedom and alpha. Then we decide whether to accept or reject the null hypothesis. This seems a little cumbersome, and it is, because this is why we have statistical software to do this for us. But just out of practice, it's a good idea to get used to looking at a calculated t-value or calculated test statistic, looking it up to see if it falls in the tails of that sampling distribution and whether or not we would reject the null hypothesis. Once you've done that a few times, you can get that kind of ingrained in your head, and then you can allow yourself to go ahead and use the computer to do it. So this is an example of critical values for a t-distribution table that we might look up values. So notice here in this table we have our alpha level, which we've set here at 0.05. Often a table will have alternative alpha levels, but we're going to mostly focus here on the alpha less than 0.05. The degrees of freedom are going to depend on the specific test that we're performing, but the degrees of freedom are generally directly related to sample size. So depending on how degrees of freedom are calculated, we're really just saying incrementally as sample size increases. Notice that the size of this critical value gets smaller and smaller as we get bigger and bigger samples. Okay, so notice that the size of these critical regions varies as the sample size increases. It gets smaller and smaller and smaller. This has to do with the area under the tails. So for a t-distribution with 1 degree of freedom, or let's say a sample size of 2 or 3, the size of those tails are huge. Okay, we're just as likely to get one value versus another value. Okay, but as we get larger samples, the size of that area under the curve in the tails gets smaller and smaller and smaller and smaller and smaller. Okay, incrementally smaller. And so you'll notice if we even jump between sample size or degrees of freedom of 13 to 28, there's just a very small incremental change in that critical value as we get larger and larger populations. At this point, when we're going up to sample size of 30, we still want to look this value up. This is going to be our way of precisely calculating confidence intervals or performing t-tests. And as we get larger samples, this value here of 2.048 will eventually kind of resolve to 1.96, and then we start to get decimals that are way to the right. And so once we hit a certain sample size, we're going to get to a value of 1.96, which we already saw earlier. In our z-distribution, in a z-distribution table, there's a single value for this alpha, it's 1.96. As the shape of the distribution starts to become more like a standard normal distribution, it's going to hit that point where the area in those tails is about the same, regardless of sample size. So we get a lot of bang for our buck, sample size wise, early relative to late. The software approach is a little easier. We do still have to select an appropriate test, a test statistic. We do also have to specify a level of significance. Often there's a default setting, alpha 0.05, 95% confidence intervals, but that does technically have to be set, and it is decided upon by the researcher. We have to decide, are we going to do a one-tail test? Are we going to only allow the difference, let's say, to be in one direction, or are we allowed to go in 2 directions? Normally, we're going to do a 2-tail test. Usually, that'll be the default as well. Specify the variables or reference values. If we're doing a one-tail t-test, we're going to just have one reference value and compare our sample to that. But we need to specify the variables. And then we run the procedure. And it's going to calculate a test statistic, the degrees of freedom, and an exact probability level. So rather than having a value that would say we reject the null hypothesis at alpha 0.05, it's going to calculate the statistic. It's going to calculate the degrees of freedom and calculate an exact probability. So an example would be, we might have a t statistic of 2.95, degrees of freedom of 18. Okay, if we were to look that up in the table, degrees of freedom of 18, our test statistic would have been 2.101. That would be our critical region. Okay, so anything higher than that would be statistically significant. In this case, we have 2.95, so it's higher. The actual p-value that we would calculate, the probability where it really falls in that distribution, would be 0.009. So quite a bit below 0.05. Okay. So we would say that only 9 times out of 1,000 would the result have occurred by chance alone. You can be fairly certain that this is not a chance finding, that there truly is some sort of difference, okay? So in this case, this would be statistically significant with an even more stringent alpha of 0.01, let's say. One of the more common hypothesis tests that we would do with our data would be performing tests of differences in group means. Let's say we have a drug and we want to say, is this new drug performing better than placebo on some outcome? And in this case, our outcome would have to be some sort of continuous measure. Let's say it's blood pressure medication, and our goal is to lower blood pressure. And so we're going to compare a new drug versus placebo or against current treatment. So we're going to have 2 groups, treatment versus control, and we want to know, are the group means different on some outcome? Okay? And we can calculate that for our sample, but what we're really interested in is, well, what would this mean in a large population? So an independent sample t-test is used when the independent variable is nominal level, in this case, treatment versus placebo, and has only 2 levels. Okay? And we have what we call 2 independently sampled groups are being compared. So by independent groups, we mean 2 different groups. They're not the same people pre and post test, they're not from the same family, not from the same household. Okay, it's 2 separate people, 2 separate groups. We have an experimental group and a control group. It could be men versus women, it could be children with a disease like cystic fibrosis, those without. Ideally, we're using this in an experimental design, but we will do t-tests for other designs as well. But it was really designed for randomized studies. So for an independent sample t-test, the dependent variable is going to be an interval or ratio level variable. That is a variable for which it is appropriate to compute a mean. So we might have weight, scores on some kind of scale, it could be a stress scale, it could be a depression scale, it could be whatever it is we're measuring. Fatigue, it could be, as I mentioned, blood pressure, any number of things. It can't be things like disease, yes, no. It can't be even something ordinal like severe, less severe. It has to be something that's either interval or ratio. The null hypothesis in an independent sample t-test, as you may have guessed, is that the 2 groups are the same, that there is no difference between the 2 group means, that the independent variable and the dependent variable are not related. Okay? We would formally state this, that the mean of one group equals the mean of the other group. That would be our null hypothesis of no difference. We could also say that mean of one group minus the mean of the other group equals 0, but that would mean exactly the same thing mathematically. So the alternative hypothesis would be that the 2 groups are different. That is, that the independent variable and the dependent variable are related, and that there is a difference between the 2 group means. Formally stated, we would say that the alternative hypothesis is that the mean of group 1 is not equal to the mean of group 2. Okay? Or we could say that one subtracted from the other is not 0. Okay? That's our alternative hypothesis. We're not saying to what extent they're different, we're just saying that they're different. So if we're testing the null hypothesis in a t-test, in a 2-sample independent sample t-test, we're testing the null hypothesis by computing a test statistic and comparing it to values of what is improbable if the null hypothesis were true. What is improbable lies in the tails of the theoretical sampling distribution. Okay, so if we get a big enough t-statistic that we calculate, it's going to be deeper and deeper into those tails of the sampling distribution. Okay, so that's how we're going to determine how likely the null hypothesis to be true. All right, so some assumptions of an independent sample t-test are that the samples are independently sampled from each other. Okay, so we're not taking 2 individuals from the same household. We're not taking the same person and observing them at 2 different time points. We're taking 2 independent groups, just like when we would randomize an experimental design, one group or to another. Okay, so they're independent. Outcome variable is normally distributed in the two populations. We can start to relax this assumption with larger and larger populations because of the central limit theorem, but for the purposes of a t-test, when we usually are talking about smaller samples, the outcome variable should be normally distributed or approximately normally distributed in those two populations. The two population variances are assumed to be equal. This is an assumption of the homogeneity of variance. We can actually formally test this as we're doing our work, and if we violate this assumption, we're not in too much trouble. We can do a correction if there is not equal variance. So that's something we're going to look at as we do t-tests. Some software, you get two different p-values based on those assumptions. In the software that we're going to use in this course, it will ask us to assume equal variance or not equal variance. And so this assumption of the homogeneity of variance is not as important in that we have a way to deal with when they're not homogeneous, but we will want to be mindful of that as we're performing a t-test. A t-test is fairly robust, meaning that we can relax certain assumptions as long as the sample sizes are relatively large. We've got more than, let's say, 40 per group, and the sample sizes in the two groups are similar. Then we can say that by rule of thumb that one group is no more than 50% larger than the other. We can relax some of those assumptions about equal variance and normality. However, for smaller samples, we're going to want to make sure that those are holding true. So in a pool variation approach, the straightforward calculation is that we're going to take the difference in the sample means and divide that by what we call the standard error of the difference of those two means. Okay? And because we're saying they're equal, there's going to be one value for that standard error of the difference. Okay? So that's a relatively straightforward calculation. If we're going to use a pool of variance, then we're going to have to do it separately for each of their variances. In this case, we're going to take the two sample sizes combined, N1 and N2, and we'll subtract 2 because we've got two parameters that we're actually estimating here for each of the two group means. If the calculated t, or the absolute value of t, is greater than the table value for the appropriate degrees of freedom in our chosen alpha, then we could conclude that the result is statistically significant. We can attest that assumption of pooled variance using what's called the Levene's test. And Levene's test actually uses another test called an F-test. And if this test is statistically significant, the variances are likely unequal, and the pooled variance formula should not be used. This is a little counterintuitive. The assumption here on the pooled variance test is that they are homogeneous. If we get a p-value of less than 0.05, that means that we've rejected the null hypothesis of no difference, in which case we will then say that they're not equal. And so just like we were being conservative before, we're going to assume that there's equal variance unless we have enough evidence to suggest otherwise. That's why we can be somewhat lax with our assumptions once we get sample sizes that are larger. We are going to want to perform a formal test on this, however, if we're using these smaller sample sizes. Levene's test and StatCrunch, you actually have to perform that as a separate test prior to doing the t-test. So you would use the stat tab, the variance stats homogeneity test, to test this assumption of equal variance. If it is equal variance, then you can check the box when you perform the t-test that yes, they are equal, use the pooled variances. Otherwise, you would unselect the box and say no, the variances are unequal. This will only make a very slight difference in the calculation of the t-statistic, but it does matter in terms of what our p-value is, particularly if we're right on the fence of what we're going to reject or not reject the null hypothesis. So we don't want to just pick and choose which one is, most convenient. We want to do this based on the rigors of the test. So we'll need to do a two-step test here with small samples and do Levene's test of variances first. We'll get some practice with that. A paired samples t-test violates the assumption of independence, and usually this is by design. Okay, so we're going to sample an individual, and let's say we sample them at one point in time, and then we want to look at them at another point in time. we're going to consider those as two separate occasions and two separate samples, but they're the same people. So paired t-test is used to test the difference between related groups or for the same people measured on the same variable twice. We call this also a dependent t-test or a correlated groups t-test. An example would be pre or post-test intervention when we have pairs that are related, husbands and wives, sibling pairs. It'd be far more common, though, that it's something that's a design issue where we purposely are looking at pre and post or before and after, maybe a crossover design. Okay, in terms of sample size, again, for relatively small samples, the tails of the t-distribution are fatter, okay, as we get smaller samples and less than 30. But you can start to see, even as we approach a sample size of 30, we start to get a more peaked distribution, similar to a normal distribution. And as they become larger and larger, they get more peaked. And the trade-offs in terms of the shape of the distribution and what the cutoff points are in the table become more similar as we get larger and larger. Okay, so there's a lot of trade-off early on in our ability to make inferences and how much evidence we would need to reject the null hypothesis. And so we get bigger sample sizes, those tails get smaller, and we can have better estimates when we're doing parameter estimation. We can also have more powerful tests. So in summary, inferential statistics can be used both for parameter estimation, so when we calculate confidence intervals, and also for hypothesis testing, when we want to say, are two groups actually different? So both parameter estimation and hypothesis testing are based on probability distributions, such as we saw with the t-distribution. A t-distribution table is used for finding critical table values of t needed both for confidence intervals and hypothesis testing. The difference will be in terms of the degrees of freedom that we calculate and what our goals are, but we are going to use those underlying t-distributions for smaller samples. In practice, we usually let a computer software perform these t-tests and calculate the confidence intervals. So in our online exercises, our class exercises, you're going to get some practice calculating all of these different types of statistics. But this was our background on inferential statistics. Next week, we're going to get into more bivariate analysis, including chi-square tests and ANOVA. But t-tests are our introduction to this idea of making inferences about a population. And usually it's an interesting question that we as researchers want to know the answer to. So that's it for now. We'll talk to you next week. Look forward to seeing you then. Thanks. Bye.